Alright, hi everybody. In this video, we'll go through E2 reactions. E2 reactions are elimination reactions, so we'll end up with a double bond, but they're bimolecular, meaning two molecules are part of the rate determining step. Here's an example, and let's just go ahead and label leaving group, electronegative atom bonded to a carbon. This is the electrophile. This is the nucleophile. Now there's this note here that the nucleophile is a strong base, removes a beta hydrogen as the leaving group leaves in one step. So looking at our electrophile molecule, our alpha carbon is the carbon bonded to the leaving group. Any carbon bonded to alpha carbon is a beta. Any hydrogen bonded to the beta carbon is a beta hydrogen. So one of these beta hydrogens will be removed by the nucleophile, which is a strong base. There's a note here that the beta hydrogen and leaving group must be anti to each other. That is anti in space, so if carbon to the leaving group is over here, this is our anti-hydrogen. So in one step, the nucleophile electrons create a bond to the beta hydrogen that will be eliminated. The electrons in this carbon to beta hydrogen bond will form a double bond between the alpha and beta carbon, and then the leaving group leaves. So we have three arrows in the same step. The products that result, we have the nucleophile, oxygen is now bonded to a hydrogen. The leaving group left, so it is Br minus. And then the carbon, this organic molecule is what we're mostly concerned about. We have a new double bond between the two carbons, the alpha and beta carbon. And then the hydrogens are still there. The leaving group has left, so our alpha carbon now just has two bonds to hydrogen. And same with the beta carbon. Now we still have sodium as a counter ion, so I'll draw that as well. You could draw this product without wedges and dashes, and it would just look like this, and that's fine as well. And so there's the E2 alkene product. Because it's one step and both the nucleophile and electrophile are part of that step, the rate of this reaction is equal to rate constant times the concentration of the nucleophile times concentration of the electrophile. And that's the E2 mechanism. Now, one thing that I pointed out and we'll talk more about is that the beta hydrogen and leaving group have to be anti to each other. Sometimes rotating single bonds is required to achieve this anti-orientation. Now here they're already anti to each other, bromine and hydrogen there. And that would be the case regardless since there are three hydrogens here. But we'll see an example where we need to do a rotation, and we'll do that soon. But one thing that we can do to make sure that leaving group and beta hydrogen are anti to each other, we've seen this word anti when we talked about Newman projections. So if we draw a Newman projection, looking down the alpha to beta carbon bond, so I'll do that from beta and then alpha behind. Looking down that bond, we'd have beta carbon in front for the Newman projection. It has, let me use some highlighting for our anti-groups. So this hydrogen that I just highlighted would be drawn pointing straight up, and then there's one pointing down and to the right, one pointing down and to the left. So there's that anti-hydrogen. And then if you draw the rest of the Newman projection for the back carbon, the bromine would be pointing straight down. Hydrogen and hydrogen. And then this is how we know which hydrogen to remove and that it's in the correct orientation. So a little note here, this is anti to leaving group. This is the hydrogen eliminated in the reaction. And then the product is just what we drew above. I'll just redraw. And then our byproducts. Okay, so that's for the reaction that we had already looked at. Let's look at this new one where we'll have to do a rotation. Now we're going to assume this goes through an E2 mechanism. If we identify leaving group, I'll highlight it here. There's our bromine leaving group. That makes this the alpha carbon. This is beta. But the group that is anti to the leaving group is a methyl. It's not a hydrogen. The hydrogen is over here. And so we need to rotate around the alpha to beta carbon bond in order to achieve anti-orientation. So if we again draw Newman projection, we can put alpha carbon in the back just to keep things consistent with our previous example. So beta carbon in front. That would make CH3 up here. Hydrogen. An ethyl group. And then for the back carbon, the alpha carbon, bromine is pointing straight down. This would be methyl. And this is ethyl. Okay, so right now, as that molecule is drawn, the leaving group and the beta hydrogen that's meant to be eliminated are not anti to each other. So we will need to rotate the back carbon. Let's say we rotate, or the front. Let's rotate the front carbon. And we'll rotate counterclockwise 120 degrees. Redrawing the Newman projection, the front carbon now has the beta hydrogen right there. That puts the ethyl group over here and the methyl over here. And then we didn't move anything in the back carbon, so we still have bromine, methyl, and ethyl. Now, leaving group and beta hydrogen are anti. So we can draw the product, and what's nice, once you get to the correct Newman projection, the groups that are on the right side of wherever the leaving group and beta hydrogen are, just on the same side, closest to each other, those are the two groups that will be on the same side of the double bond. So now we're drawing the product. We've got these two products on the same side of the double bond. And then we can say the same for those two groups, not the two products. Those two groups are on the same side of the double bond. Same thing here. We would have the ethyl up here and the methyl down here. This allows us to draw the correct product because without rotating to get the leaving group and beta hydrogen anti, you may have drawn an E alkene when it should be Z or a Z alkene when it should be E. In this case, our priority groups are the two ethyls. They're on opposite sides, so this is an E alkene. And this is the only product that forms. The Z alkene doesn't form. Okay. Now, if you're drawing the actual mechanism, you can draw just on this structure, right? So those three arrows, but the proper product has to be the E alkene for this mechanism. So that's one thing to consider when you're looking at the E2 reaction, just to make sure the beta hydrogen that's getting eliminated and the leaving group are anti to each other. Okay, on the next page, I have this flow chart, and I asked you all to draw and write in these notes already. So I'm just going to talk through, I'll use my laser pointer to talk through how to follow this flow chart. In this chapter, we've learned about 4 different mechanisms to our substitution, to our elimination. They all begin with pretty similar starting materials. We have an sp3 carbon bonded to a leaving group, and we have a nucleophile. Depending on properties of those two molecules and the solvent, we can better predict which mechanism is most likely and which products are going to form. So this is if you're not told which reaction to focus on. A lot of times, like for example, right here, it says draw the E2 product. So you don't even have to worry about going through the flowchart if you're told which reaction it's going to be. But sometimes you're not. And for example, if you're going through a lab, it might not tell you. If it's a new experiment especially, nothing's telling you what reaction is going to occur. So we have to use these predictions or these properties to predict which mechanism and product will form. So there's really 3 options to start off with. Now one of these, the carbocation, can give us 2 more. But this is just to give a framework of what to look at. We're talking about the alpha carbon, the nucleophile, and the solvent. If the alpha carbon is primary or secondary, then it's most likely SN2 or E2. If it's tertiary, or if it's stabilized by resonance or a hydride and methyl shift, then the first thing that will happen is carbocation formation. So that's the first thing to look for, is your alpha carbon. Is it primary or secondary? If it is, and it's not stabilized by resonance or shifts, then you're most likely going to debate between an SN2 or E2. If it's tertiary, then that's SN1 and E1. Okay, let's focus on SN2 and E2 for now. The biggest difference between these two mechanisms are the nucleophile. E2 reactions occur with a strong base. The nucleophile is a strong base. I'm going to scroll up and explain why. Remember what bases do? They take a hydrogen from an acid. So if this nucleophile is a strong base, it's more likely to remove a beta hydrogen than what happens in SN2, which is the nucleophile just bonds directly to the alpha carbon. So when you have a strong base, more likely to remove that hydrogen and go through E2. So these are negative oxygen, negative nitrogen, a lot of negative carbons, and this is even more likely than SN2 if the nucleophile is big and bulky. When it's large and there's steric hindrance, that makes it difficult for the nucleophile to do what a nucleophile does in SN2, which is bond directly to the alpha carbon. So if it's large, negative oxygen, nitrogen, most carbons, then E2 is more likely. We see SN2 more often when the nucleophile is a halogen, or if we have a neutral nitrogen, phosphorus, sulfur, oxygen, these neutral, negative halogens or neutral other nonmetals. Notice these are all negative except for, the halogens would go through SN2 because those are really, really, really weak bases. And then SN2 and E2, they both most often occur in polar aprotic solvents, but polar protic is possible. And then one extra note is that E2 can only occur if beta hydrogens are available. If there are no beta hydrogens, then there is nothing to eliminate, and E2 cannot occur. It would have to be SN2. Okay, so that's if you have a primary or secondary alpha carbon. If it is tertiary, or if it's not tertiary, but it's stabilized by resonance, hydride, or methyl shift, then a carbocation is what's going to form first, and that can lead to both SN1 and E1 reactions. For these reactions, the nucleophile is usually the solvent, so that is usually an alcohol or water. These are polar protic. They stabilize the carbocation. And we can assume a mix of SN1 and E1 products as long as beta hydrogens are available for the E1 reaction. Okay, on the next page, we have some examples trying to identify what type of reaction is most likely based on the alpha carbon, nucleophile, solvent, and then drawing the reaction mechanisms.